Thank you all for attending this talk in the Applied PD seminar this week. The speaker this week is David Nicholls from University of Illinois at Chicago. Known Dave for over 20 years now. So Dave got his PhD at Brown University under the direction of Walter Craig. And after a postdoctoral stint at University of Minnesota, he joined the faculty at Notre Dame University. Then after some years there, he moved to University of Illinois Chicago, where he's been since then. And today he's going to talk to us about launching graphene surface plasmon waves with vanishingly small periodic grating structures. Thank you, Dave.
Thank you, and thanks, Bernard, for the invitation, and Jorge for helping me get this all set up. It's really a pleasure to talk to you guys today about all of this. And yeah, so I'll tell you.
Sorry, can you try Command H?
I'll try Command H. Did something good happen?
No.
No. Well, you guys all disappeared. Should I now try and go into full screen mode?
Or I thought that read mode under before full screen mode.
So did that work? Can you now see my talk?
Nothing changed for me.
Nothing changed for you. Okay. Maybe I'll just go with what I'm familiar with. This is how it works when I teach. So I'll go with that. Right. So there's a number of collaborators on this project, and the most important one is Sang-Hyao No, who's in electrical and computer engineering at the University of Minnesota. And really, it's his questions which have driven a lot of this and other research projects. And I'll tell you about what his question was in this particular instance in just a moment. Other collaborators are my former PhD student, Jin Tong, who's now at Marquette, and then one of our postdocs here at UIC, former postdocs, Young-Jun Hong, who's now at San Diego State University. So the NSF is occasionally very generous. And there's some references here, and if you're interested, I can point you towards those at the end of the talk, or if you contact me by email. This work is currently submitted, but I want to talk about two projects. And the first one I want to talk to you about has already appeared. So I'll go into all of that. So nanoplasmonics is this fascinating field, which has now been around for a little while. And back in 2011, this fellow Stockman sort of summarized what the state of the situation was. And in short, nanoplasmonics is the study of optical phenomenon in a very small vicinity of a metal interface, a nanoscale vicinity of a metal interface. And the fundamental question is, can you concentrate radiation, electromagnetic radiation, into a very, very small area, space? In particular, can you make it smaller than half the light's wavelength? So this is concentration beyond what you could reasonably expect from the radiation that you're illuminating with. And so the answer to this question is, well, it depends on what your structure is made up of. And if you have a conducting metal, gold or silver, then in fact this can be accomplished. And so somehow the story is that you have a plain electromagnetic wave driving the free electrons in the middle. So you have to have electrons that are free to move around. With respect to the ion lattice, it generates a charge and a restoring force. And this oscillator has a quanta, a so-called surface plasmon, or they also talk about volume plasmons inside the metal. And so a surface plasmon resonance is a resonance between these plasmons and the incident radiation. But in the end, what you're looking for is you're illuminating with plane wave radiation of some wavelength, some frequency, and you would like to excite a wave, surface wave, that's bound in a very small vicinity of the interface between your dielectric, maybe vacuum above, and the metal, which constitutes the grating. And so if this happens, cool things happen. So what's one way to express what the cool things are that happen? Well, one thing you can do is you can study what we've called a reflectivity map. And here's a nice picture of one here at the top of this slide. And what are you meant to look at? So along the x-axis is lambda. So this is the frequency, as the wavelength of the illuminating radiation. And then along the y-axis is h, and that is the height of the grating profile. So as we'll see in just a moment, as you see from this plot, when the height is 0, nothing interesting happens. You just get white. I'll explain what white is in just a moment. But as you make h bigger, interesting things can happen. And so you can think of h as the thing multiplying, say, cosine of 2 pi x over d. So you've got a corrugation to your grating, which is characterized, shaped by, say, the cosine or the sine function. And this h is just the amplitude. And then what are we measuring in this contour plot? Well, we're measuring the reflectivity. So what fraction of the energy that you have put into this structure is getting reflected back to you in the far field? And so if you're at white, then, well, it's at least 90%, probably 95%, or even higher. So gold or silver is a little bit lossy, so you'd expect that you're going to lose a little bit of energy. But for the most part, throughout this plot, everything that you send in is coming back to you, with one notable exception. And so that is right around, I don't know, 670, 675 nanometers. Those are the units along the x-axis, around a height of 100 nanometers. You see a precipitous drop in the reflectivity. And so not only are you not seeing 95% reflectivity, you're not seeing 50, you're seeing maybe 10 or maybe even less % of the energy that you sent in coming back to you in the far field. And so you could wonder, well, is that all really just lost energy to the metal down in the lower layer? Well, in fact, it's not. Some of it is, but it's mainly exciting a surface wave which propagates, transversely, not coming back towards you. And so this is an interesting phenomenon, but the engineers in their genius have figured out how to do something cool with this effect. So the thing you need to notice, first of all, is that it's an enormous drop, 100% down to 10 or maybe less %. So the response is very noticeable. But secondly, it only occurs over a very narrow band of wavelengths. So if you stare at h equals 100, when lambda equals 650, well, you're getting almost 100%. You can see my little hand. Almost 100% reflectivity. And again, if you go over to 700, or maybe 725, again, for that height of 100, you're getting most of the energy reflected back. And in particular, the very, very deep trough that you find yourself in, where you really drop off, that band of wavelengths is, I don't know, maybe 25, 20, 30 nanometers wide. So it's very, very sensitive to the wavelength of light that comes in. You don't have to use wavelength. You could also use angle of incidence, and you'd see something similar. And so the engineers have noticed this and designed tests based on this phenomenon. And so the trick is to do the following: design a grating structure which has this sort of behavior, and then take that very same structure and build it in such a way that if something reacts with the structure, perhaps you have a very thin layer of reagent on top of the gold, that this picture can change significantly in the presence of some sort of reaction, biological or chemical. And so this, in fact, is the technology behind the pregnancy test. You have a structure with a reagent, and if you produce a sample, some urine from a woman who is not pregnant, that it doesn't contain a certain hormone, and there's no reaction that happens, and you get this plot that you were expecting. However, if the urine contains the hormone that indicates that a woman is pregnant, then this shifts, and the precipitous drop occurs, well, not at 650 or 670, but perhaps 720 or 620. And so it's very easy, with a very strong response, to see the difference between a reaction took place and a reaction didn't take place. And so sensors which work in this way are called SPR sensors, surface plasmon resonance sensors. And in this paper from 2008, Homala lists several hundred tests that are built upon this technology. And so once you have the physical phenomenon that happens, and you have the capability of building such structures, which I should note are very, very small. I mean, everything is on the order of nanometers, so this does not need to be a big device. Then the trick is really just cooking up the right reagent layer that is going to react with what do you want to detect? Do you want to detect toxins or hormones? Do you want to detect cancer markers or the presence of drugs, heavy metals, phenols? And if you can get that sorted out, well, then you've got this sensing modality, which is highly accurate, highly sensitive, and by now very well understood. So these are really interesting structures that it would be great to be able to simulate. But now there's a couple of characteristics of these things that you need to keep in mind before you start building them and before you start thinking about simulating them. And so the first is that if you have a structure which has just got 2 layers, then you cannot excite a surface plasmon resonance if the interface between the 2 is flat. So you can write down in this case what the sort of exact solutions are, the Fresnel coefficients, and as you change the wavelength lambda, you know, the values of the reflectance and the transmittance change, but you don't see this gargantuan drop in the reflectivity. And so somehow there's insufficient momentum. And so what you have to do is change things a little bit so that your sensor, so that your structure can generate this response. And there's a number of ways of doing it. One way is to add a 3rd layer somehow. But an easy way to do it is to add corrugations to the interface between the upper layer and the lower layer. And periodic corrugations are what you're after. And they can be quite simple. They can just be sines and cosines, or they can be things that are more like periodic binary profiles. What works best in our simulation strategy are just sines and cosines. The second thing to realize is that the size of the deformations, the amplitude of the corrugations, doesn't need to be large. And in fact, if it gets too big, other nonlinear processes kick in and you don't see this response. And so it sort of quenches after a while. So you need small deformations. And now the question that Seng-Hyun came to me and collaborators like Fernando Reitig, who used to be at Minnesota, is, you know, what are the limits of this? So flat is too small. And if you get up to 100 or 150 nanometers as the amplitude in the previous example, that's certainly big enough so that you can notice a response. But what if the interface perturbation was only 50 nanometers or 10 nanometers or 5 nanometers? Well, you know, it's an interesting question, sort of philosophically, I suppose, but Seng-Hyun had a very specific purpose in asking this question. And it's the following. If you use sort of standard technology, so standard technology is still quite intricate, then typically you can expect an error in your measurement for how you've deposed your layer of gold or silver to be on the order of plus or minus 5 nanometers. And so in particular, if you are someone who are using a standard technique to make a flat gold surface, you claim it's flat, well, really, you can only claim that it's flat plus or minus 5 nanometers versus a lengthwise scale of maybe a micron or maybe 500 nanometers. And the reason Seng-Hyun was interested in this is because he and his collaborators had developed more advanced techniques, such as this method of template stripping, which I talk about here in the final bullet point, where you get things that are much, much flatter, not flatter, guaranteed to be flatter than the typical approach. And so in particular, if you check out this article that they published in Science, they can get tolerances down to a nanometer or even half a nanometer, so on the order of angstroms. So it's a fantastic technique. I don't know how they do it, but they are able to produce guaranteed ultra-flat interfaces. And so he wanted a selling point for his technique. And so one way to sell this is to say, okay, you think that with your method you can generate something flat, but I claim that it's not flat enough. How can you say that it's not flat enough? Well, one way is to say, okay, your purportedly flat interface is generating a surface plasmon resonance. And we know that that's not supposed to happen if it really were flat. And so if you have a perturbation on the order of 5 nanometers, what sort of response do you get from the interface? So you'll have probably a little bit of absorption, but is it just a 1% dip? Is it a 50% dip, or is it something in between? And so what we found with a numerical simulation that I'm about to tell you about is that in fact, with only a 5 nanometer perturbation on a period about 500 nanometer cosine, there was a drop in the absorption, a drop in the what you see in the far field of about 20%. And so we really found that to be quite sizable and noteworthy. And so that's part one of what I'm going to tell you about. Part two is, okay, never mind metals. Metals are great, but now the field is sort of moving in the direction of including the so-called two-dimensional materials into grating structures. And the most famous example of this is graphene. There are other ones, but graphene is one that's been around a long time compared to the other materials and is relatively well understood. Let's see what happens if you take flat graphene and perturb it just a little bit. What sort of response do you notice? And so hopefully by the end of the talk, I'll come to that. All right, so we should write down just a little bit of a mathematics. What's the geometry of our configuration? Well, here's a picture. We've got a dielectric above, say vacuum or air, or maybe water, if we're thinking of doing some diagnostic testing. And then down below, at first we've got a metal, which is going to be some sort of lossy material, and you're illuminating it from above by plane wave incidence. And just to make things simple, let's suppose that it is normally incident. It's not a requirement, but it will make our lives simpler. And in general, what's going to happen is stuff is going to be reflected back up, and then stuff's going to transmit. Although if it really is a metal down in the lower layer, it's just the energy is going to decay away rather rapidly. Now, all these effects are not particular to a fully three-dimensional simulation. And to tell you the truth, typically the engineers just focus on a 2D simulation because it's a lot easier. And really you don't, well, you can get other effects in 3D, but a lot of the most famous effects you can already see in 2 dimensions. And so what do we mean by 2D? Well, in the X and Z directions, there's certainly variation in the profile and the value of the permittivity. But in the Y direction, pointing out of this slide, out of your computer screen, things are invariant. And so all of the quantities in question are just going to depend on X and Z, but this does have implications if you align the incident radiation in just the right way, so that things are pointed in either the transverse electric or transverse magnetic direction, then in fact the vectorial Maxwell equations simplify to scalar equations. So really there's a lot of simplification that happens when you have things invariant in one direction. So the layer interface is going to be shaped by the function g of x, z is equal to g of x. That's going to be periodic of period d, and this is going to give 2 domains, su, which is above g, and sw, which is below g. And why u and w? Well, when we first started writing down the equations, there was a middle layer as well, so it was u, v, w. You're sort of running out of letters. So u for upper seems to make sense. Why it's w is a little unclear, but it is, and it's too late to change now. Each layer has a permittivity, epsilon u and epsilon w, giving rise to an index of refraction. Epsilon u is going to need to be a positive real number so that the plane wave can transmit through it, propagate through it. Epsilon w could be a real number, in which case it's a dielectric as well, but it's going to be complex valued if you're trying to study gold or silver, as the lower layer. And so we illuminate from above with monochromatic plane waves of frequency omega and wave number omega over Cu, where Cu is the speed in the upper layer. And this incident radiation has the form of a complex exponential, e to the I minus omega t plus alpha x minus gamma u z, where alpha is Ku sine theta and gamma is Ku cosine theta, and theta is going to be 0 in this talk. And the unknowns are the transverse components of either the electric or the magnetic fields, where you have reduced things, you have factored out the time dependence, because it's a nice linear problem. And if you illuminate with time harmonic radiation, what will be scattered is time harmonic radiation of the exact same frequency. Now, solutions to the governing differential equations are not going to be periodic necessarily, although in the case when theta equals 0, they will be. In general, they're going to be quasi-periodic. So if you go along 1 unit in the period in x, you won't necessarily get back to where you started. You get back to where you started times this exponential factor, e to the I alpha d. And notice that the plane wave that you illuminate with has this property. And then from the show it to you in just a moment with the Rayleigh expansions. But basically it boils down to the correct periodic dependence in the z direction or boundedness, depending on what sort of solution you have. Or maybe it's easier with mathematics. The final boundary conditions that you need is some sort of continuity of the electric or the magnetic field at the interface. And so in the absence of surface currents, so if you're not modeling graphene, that's how we're going to model our graphene, then you have continuity of the tangential components of the electric and the magnetic fields. And so if you put this all together, you arrive at the following system of partial differential equations which govern these transverse components of either the electric or the magnetic field. So it's basically a Helmholtz equation, but I've written things carefully in terms of divergence of the reciprocal of the permittivity times the gradient of the field quantity, either U or W. So U for the upper layer and the W for that lower layer SW. Quasi-periodicity of U and W, somehow outgoing conditions on U and W, upward propagating for U and downward propagating for W, and then boundary conditions which couple these guys at the interface, Z is equal to G of X. And so the first condition is a Dirichlet condition, which says that the field is continuous at the interface. So the jump in the scattered field above to the scattered field below is given by the incident field, or the opposite of the incident field, at Z is equal to G of X. So that is Xi. So this is the total field at the interface is equal to 0. So scattered field U plus incident field Ui minus the transmitted field is equal to 0. And then the second condition is where you notice the difference between the two polarizations. So this is a Neumann condition, sort of an impedance condition, which tells you how the normal derivative jumps. Now, because the permeability, mu, is the same everywhere in the structure, you do have continuity of the normal derivative at the interface. And so that corresponds to transverse electric polarization. The normal derivative of U minus the normal derivative of W is equal to the opposite of the normal derivative of the incident radiation at the interface. But in transverse magnetic polarization, you have to take into account that there are different permittivities as you go from one layer to the next. And so that jump in permittivity gives you a jump in the normal derivative. And so you get this coupled set of Dirichlet and Neumann conditions. Now, there's a number of ways that you go about trying to find solutions to that collection of partial differential equations, say numerically. And it seems like the most straightforward thing to do would be to set up some sort of finite difference or finite element simulation. And certainly that's what a lot of people do. And there are many groups, particularly in engineering departments, who just sort of outsource this to black box solvers like COMSOL or some other finite element software. And that's fine. You plug in all of your different parameters of the things that you want to build your structure out of, and you push a button, and then you go out for a coffee, and I don't know, several hours, several days later, out comes the solution to this problem. So, you know, these solvers are great. They can solve kind of any problem you want to cook up. It's just that they may not be very efficient. And at times, it's really important to be very efficient, particularly if you want to do things like design or optimization. And so what we're going to try and do, or what we've done, is to not use such a brute force approach, try and do something a little bit more elegant, and take advantage of the fact that while this is a fully two-dimensional problem, really all you need are the values of the field at the interface. And if you had these, then you could recover the fields anywhere away from the interfaces using some sort of appropriate integral formula. And so for this, we take the following point of view. Let's take the field U at the interface, it's the trace, and call that capital U. So anytime I go to the interface with a trace, I sort of capitalize the letter. So U at the interface is capital U. W at the interface, coming from below, is capital W. And then you need two other quantities to satisfy the boundary conditions. You need the normal derivatives from above and below. And just to have a nice consistent way of formulating the problem, we always use outward pointing normal derivatives. And so in fact, when you come to the interface from above, computing the normal derivative, it's minus the partial with respect to n of u, because n itself is upward pointing. And so we call these two quantities u tilde and w tilde. And so there's this understanding that these capital letter quantities don't just come from anywhere, that you have somehow solved the Helmholtz equation associated to u and w with all of the different conditions like the quasi-periodicity and the upward or downward propagating boundary conditions. And so if you take this all into account, then really the set of governing equations just boils down to the following two equations we have here in the fourth bullet point. Capital U minus capital W is equal to Xi, this data, the incident radiation at the interface. And then the second equation is, well, it's the jump in the normal derivatives. So if you take into account all of the minus signs, it's minus tau U, U tilde, minus tau W, capital W tilde, is equal to tau U mu. And so this tau again changes as you go from transverse electric to transverse magnetic polarization. And so this is great. The governing equations have now been boiled down to two sort of interfacial equations, and your unknowns just depend on x. They don't depend on z, at least not directly. The problem, of course, is that you have two equations, but you've got four unknowns. And so it seems a bit hopeless that you're ever going to be able to find a unique solution until you realize, of course, that u and u tilde are not unconnected. In fact, they're very closely connected. Once you have capital U, together with the Helmholtz equation and all the other side conditions, then u tilde is uniquely defined. So you can compute little u and then compute this normal derivative. And so this operation of going from u, capital U, to capital U tilde is a Dirichlet Neumann operator. And so we're going to use those to close this set of equations. And a quick definition is that if you satisfy this Helmholtz equation for z above g, and set capital U to be the Dirichlet data at z is equal to g, couple it with the quasi-periodic boundary conditions and the upward propagating conditions, then there's a map, capital G, say, which takes capital U to capital U tilde. And similarly, there's a map which takes capital W to capital W tilde in the lower layer. Let's call that guy J. And these operators depend on a number of things, but one thing in particular they depend on is the shape of the interface, little g. And we'll take advantage of that in the coming slides. So in order to introduce some notation, to explain what we mean by the upward and downward propagating conditions, and to compute these Dirichlet Neumann operators in a very simple configuration of a flat interface, let me discuss the Rayleigh expansions briefly. So if the interface is flat, so that G is identically 0, then you can write down the solutions of these Helmholtz equations using separation of variables. So if you are alpha quasi-periodic, then you can express these functions, little u and little w, as Fourier series, sort of generalized Fourier series, Floquet series, I suppose. And the x dependence is as e to the I alpha px. So if things were periodic, alpha p would just be 2 pi over d times p, but because you want alpha quasi-periodicity, you add in an alpha. So that turns out to be the right or span-wise dependence for x, e to the I alpha px. And then if you demand that you solve the Helmholtz equation, you have this relationship that you've got e to the I alpha px plus, or times e to the something times z, and that something, well, let's call it I gamma u, or I gamma w. And to solve Helmholtz's equation, it has to be the case that alpha p squared plus gamma p squared has got to be k squared, where k squared is the permittivity epsilon times k naught squared, the sort of wave number in free space. And so you can solve for this coefficient in front of z, the gammas, and let's see, there's some possibilities. It is plus or minus the square root of the k squared minus alpha p squared. So just to set a precedent, let's choose the positive root, why not? But let's also notice that this epsilon k naught squared minus alpha p squared, well, for small values of p, that's going to be a positive number. And so the square root gives you a nice real number. However, if p is bigger, then that number is negative. And so you can pull out the -1 and you get I square root of alpha p squared minus epsilon k naught squared. And so there's two cases. Either the gamma is real, in which case you're in the set script u. Otherwise, it's imaginary, pure imaginary, for p's not in the script u. And now you need to study what the solutions can look like. And so there's a plus sign here in the expansion for u in front of the I gamma z. And the reason is because minus would also be a solution. But if you choose minus, then not only are waves downward propagating in the upper layer, they could potentially be exponentially growing. And so by making this choice with the plus sign in front of the I gamma p u and the plus sign in front of these square roots, you are choosing bounded upward propagating solutions. And so for this reason, in the expansion for w, you pick the minus sign. And so these guys are automatically alpha quasi-periodic because of the x dependence, and they satisfy these upward and downward propagating conditions in the z direction. And then the only thing that you don't know are the Fourier coefficients, the Floquet coefficients, I suppose, the u hat p and the w hat p. And those would come from boundary conditions. If you chose the u hat p's, little u hat p's, to be capital U hat p, the Fourier coefficients of capital U of x, then if you evaluated at z is equal to 0, then you would recover capital U. And now you can compute the Dirichlet Neumann operator, in this case, by just computing the normal derivative, pointing downwards. In the flat interface case, it's the minus z derivative, and that gives you a formula for the DNO G, which is expressed right here. So it's this sum on p's, wave numbers, minus I gamma p u times capital U hat p e to the I alpha px, which looks really foreign until you think about what would the formula look like if I took a regular derivative of the function capital U, which was expressed as capital U hat p e to the I alpha px. Well, if you just took a classical derivative, that would pull down an I alpha p in front of the Fourier coefficient, the Floquet coefficient, and that doesn't look so strange. And so this is a generalized version of that, where rather than multiplying by alpha p, you multiply by minus I gamma p. And as p goes to infinity, alpha p behaves like a linear function. It basically behaves like 2 pi p over d. Gamma p also has similar behavior as p gets very large. And so you can think that I gamma p, or minus I gamma p, is like a first derivative operator, except it's highly non-local. And so for this reason, we use this notation, minus I gamma d applied to u. The same sort of thing holds for capital J. And these two operators are Fourier multipliers. They are diagonalized by the Fourier transform, and they're order 1. They grow like p to the first, and so you can think it's like they take a derivative from either capital U or capital W. Now, never mind exactly what the definitions are for these Dirichlet Neumann operators. In terms of them, the surface governing equations can be written quite simply as a linear system, AV is equal to R. So V is our collection of two unknown functions, capital U and capital W. A is a linear operator, a linear differential operator, 2 by 2, identity minus identity in the first row, and then tau U G, that Dirichlet Neumann operator in the upper layer, tau Wj, the DNO in the lower layer, and then on the right-hand side is the data, Xi and minus tau nu, and I've actually multiplied the second equation by -1 to get this particular form. And so our computational strategy is the following. We just want to solve AV is equal to R, and we have an advantage over finite difference and finite element methods because our unknowns, U and W, only depend on the X variable. So we have far fewer unknowns than a finite element or a finite difference simulation. The trick is we somehow have to invert A. And one thing to try is a collocation approach. Just evaluate that A at grid points and then invert the thing. Well, the question becomes, how do you compute the G and the J? And that's one approach. Or we take a perturbative approach. And so you say the following. Everything in sight depends on G, the interface. Well, what if G is not a big perturbation of something flat? Flat is something that we can work out explicitly. And we were told at the start of this talk that the corrugations don't need to be very large in order to notice this plasmonic effect. And so maybe all of these quantities depend on the size of the perturbation in a nice way. Perhaps they're analytic in that perturbation parameter. And we could do regular perturbation theory, expand a couple terms out, and get convincing results. And in fact, that's exactly the case. And our numerical strategy is extremely rapid. And because it's sort of based on a spectral method, by the way we've expanded things in this Rayleigh expansion, it's going to be very, very accurate. So quick and accurate always works. And so that's sort of what I state here. So we're going to assume that G is equal to epsilon f. So G is a function, f is a function. F is going to be order 1, sine or a cosine or something like that. And it's the epsilon that's going to be small. And as with any perturbation argument, you initially assume that epsilon is very, very small. And then you have to go back and decide, could epsilon be bigger? And in fact, you can go back and prove a theorem that says, in fact, that epsilon can be arbitrarily large, provided that it's real. So there's a disk of analyticity of all the functions in sight. in a neighborhood of the origin in the complex plane. But in fact, if you choose any point on the real axis, you also get a disk of analyticity. Now, as you get further away from the origin, the radius of that disk gets smaller and smaller, we found, but there's always a non-zero disk. And so in theory, you can do this for perturbations as large as you'd like. Now, in practice, getting good numerical results, that's another matter, but I'll talk about that in just a moment. But the theory says that if F, the perturbation, is smooth enough, so C2 is certainly good enough, and it results in a proof which is really rather straightforward, then you get all of the results I'm about to discuss. But in fact, F can be rougher than this. It can be C1 alpha. You can even get it down to Lipschitz continuous. And all of this is going to work. It's just you have to write a much longer paper. With this smoothness, it can be shown that the Dirichlet Neumann operators, G and J, which depended on little g, and so little f, and the data on the right-hand side all depend analytically upon epsilon. And so everything in sight, the capital G, the capital J, the Xi and the nu, the boldface A and the boldface R can all be expanded in Taylor series, which converge for epsilon sufficiently small. And now we can ponder, we can postulate that, well, maybe the solutions are also analytic in epsilon. And based on the analyticity of the Dirichlet Neumann operators and everything else in the previous bullet point, in fact, you can show rigorously that, in fact, these functions are also analytic in this parameter epsilon. And I don't necessarily want to talk about that proof today. It's actually not all that surprising, given what we know in this story about high order perturbation of surfaces methods. It's just regular perturbation theory. And if you use some of the nice properties of L2-based Sobolev spaces, the proof comes out actually rather quickly. What I want to focus today is on this question that Sang-Yan had for us. Is there a way we can show quickly and accurately that, in fact, very, very small perturbations to the flat interface configuration give rise to relatively large plasmonic responses? Meaning that it really is worth your effort to use their technique to get very, very flat interfaces. And so how can we do this? Well, we're going to take the solutions, U and W, and approximate them by a number of truncations. The first is to truncate the infinite power series by some of the first 0 to n many terms in the perturbation expansion. And then each of these terms, the UNs, each of the corrections, we're going to approximate by a truncated Fourier series for each of these guys, where you just keep the wave numbers, your wave number 0, of size nx. Well, nx over 2 is what you need to keep. And in fact, you need to go from minus nx over 2 up to nx over 2 minus 1, if nx is an even number. And now we're going to approximate these U hat np's by using a spectral method, by using a collocation approach. So because everything's periodic, we're going to use a Fourier spectral method. And the right collocation points to use are the equally spaced grid points. So xj is d over nx, the spacing, times j. And now you write down a system of equations that need to be solved, the governing equations evaluated at these xj's, and this gives us a linear system of equations for the U hat np's at every perturbation order. Now, something you wouldn't think of until after you've found the coefficients and attempted to sum them is, what's the best way to sum up this truncated Taylor series you have in the first bullet point? Well, it doesn't seem like you've got any options. I mean, you just sum it up as it is. You start at 0 and you add in the n equals 1 term and the rest. And so this approach is what we call direct summation. And this is fine, but this only works if you are inside the disk of analyticity centered at the origin. And we suspect that you should be able to sum this for values of epsilon outside this disk as long as you're on the real axis. So a numerical analytic continuation. People have thought about this for a long time, and a number of techniques have risen to the top. And the one that has worked the best for us is the so-called method of Padé approximation, where you take this truncated Fourier Taylor series and approximate it by a rational function, the quotient of two truncated Taylor series, I suppose, where the sum of the degrees of the polynomials in the numerator and denominator equals n, the power of the polynomial on the left. And so this is a famous method. It's been around for over 100 years. And there are convenient formulas for recovering the b's and the a's, the coefficients of the numerator and denominator polynomials, in terms of the fn's. Now, these aren't necessarily the most stable recursions numerically, but they're fairly well understood. And they work quite well, as I'll try and convince you in just a moment. And so, given this sort of brief description of what a numerical method could look like, let's investigate this surface plasmon resonance phenomenon. So let's illuminate from above with normal incidence a structure which has got a profile G is equal to, and now because of the plots that I made, I'm not going to call it epsilon f, but h times f, where f has got this funny form which looks like this. It's a lamellar profile. This combination of hyperbolic tangents is centered at, well, the sort of d over 2, and the width is given by capital W, which is not the variable that I defined just 10 slides ago. And sigma is sort of the sharpness of the jump that you make. And so this approximates the sort of thing that Senghan and company can build in the lab. They typically make something very, very flat and then put a very thin strip on top of that. And then we took 32 Fourier modes, 32 collocation points, but to tell you the truth, that was overkill. And we only took 2 perturbation orders. It's so fast, it really doesn't matter if you choose nx to be 8 or 16 or 32. And we just picked 32. And we measured the following quantities: the reflectance and the absorbance. So the reflectance comes from summing up the efficiencies, which are these E's. And the absorbance is 1 minus the reflectance minus the transmittance. And somehow we're running a little low on time, so let me just report what we learned. Well, we learned the following. So we studied, so B is really the absorbance. So many apologies for changing notation. This is taken directly from the paper. And what we studied was this absorbance for the largest profile, or the absorbance, as a function of h. So we chose h is equal to 0, which would be exactly flat, and you get this black line where you just get, oh no, this is the reflectivity, sorry. Everything gets reflected back from the interface. Really, you can't see the difference between 1 and, I don't know, 0.999, which might happen because you get a little bit of absorption, a little bit of dissipation because of the gold. And then you bump up the profile height to 1 nanometer, 2, all the way up to 5 nanometers. By the time you get to 5 nanometers, you do see a significant dip of about 20% right around this wavelength of 555 nanometers. And so the point is that if you use Senghan's technique for making something very, very flat, the response you would get would be somewhere between the black curve and the red curve. So you might notice a little bit of a dip, but it's really going to be very, very small, maybe 1%. Whereas if you use the standard approach, it could be that you'll notice a response on the order of this light blue curve. And so you were expecting something flat, you were expecting to see something like the black line, and you've seen something very, very different. And so it really pays off to use Senghan's methodology. Now, I kind of want to wrap up here a little bit. But I did just want to say that we repeated these calculations in the presence of two-dimensional materials. So these layers of graphene. And a lot of what I just said remains the same, but somehow the governing equations are a little bit different because you include a current which modifies one of the boundary conditions. And so here's how they modify. So rather than having u minus w is equal to c, and the normal derivative difference is equal to nu, you get these extra terms, which come from the surface current. And so it's a funny thing. It's a normal derivative of w in the first equation, which is a Dirichlet condition, and then just w in the second equation, which was your Neumann condition. But these two terms don't appear in both polarizations. So the B term only appears in TE polarization, and the A term only appears in TM polarization. And so we studied TM polarization, and we noticed the following results. So we studied 3 configurations. The first was where you had freestanding graphene. So there's vacuum above, vacuum below, and then a layer of graphene in between. And now you're going to study what happens as you make this graphene more sinusoidal. And so as we varied the size of this graphene to have amplitude 0 up to 5 nanometers, is that you did notice a plasmonic response, but it was very small. It was only 1%. However, if you changed the lower level material to be an ion gel, so vacuum, graphene, and then this gel beneath, then you could notice quite a big response, about a 45% response. And this was made even more pronounced when you mounted it on silica. And so again, the point is, you have some technique for trying to mount graphene on a silica slab, which is meant to be flat. Is it flat, or does it have little corrugations because of your technique for, trying to peel off the top layer of silica so that it's exactly flat? Well, if you don't get it exactly flat, if you only get it flat plus or minus 5 nanometers, you can get these plasmonic responses, which are over 50%, when you should be expecting no response whatsoever. And so the take-home message would be that it's very important to use these techniques that Sang-Han and his collaborators have developed for making these ultra-flat interfaces. But I think it also makes a case for our numerical approaches, which can deliver numerical approximations of these configurations very quickly and very accurately, so that you can now take this computational capability and use it to design structures that have the response that you want in order to optimize structures to do exactly what you desire. And so, yeah, maybe I'll stop there. And if anyone has any questions, now would be the time. Thank you very much.